So we already did basics of circular motion. Remember that speed is equal to 2 pi times the radius divided by the period, because that's the circumference one time around the circle, and the period is the time for once around the circle. We got from that the centripetal acceleration is the speed squared divided by the radius. Remember this C, centripetal, means towards the center. So I really shouldn't have to make a video on this because there's no such thing as centrifugal force, and centripetal force is just another name for net force. Centripetal force equals net force that causes circular motion. If you have heard of it, centrifugal force is a result of inertia. That's the force you feel, like it's what you think you feel when your car turns to the left and you feel pushed out to the right. So people say centrifugal force, it's pushing you out to the outside of the circle. No, it's not. Your body is trying to keep going forward while the car is turning to the left. So no, that's inertia. So centripetal force, net force that causes circular motion. So really, you just need to draw careful free body diagrams and remember where the center of the circle is. So I'm going to do some examples. For the first one, if we have a string on a rope and we are swinging that in a vertical circle, so up and down, so high, low, high, low. When we are at the bottom of the circle, the top of the circles, or the middle of the circle, is up here, so that's where the center is. So I'm going to write off to the side, the centripetal acceleration is upward. Now of course there's gravity, downward, and the rope, so we have tension. The tension, if you're at the bottom, the rope is above it, so it's pulling upward. And we need to have an acceleration towards the center of the circle. So we need to have a net force towards the center of the circle. So the tension is greater than the force of gravity when we're at the bottom. At the top, we're at this location. The center of the circle is down here. So our acceleration is towards the bottom of the page. We still have gravity, and the rope is beneath this. So here, the net force would be the tension minus the force of gravity. Here, the net force is the tension plus the force of gravity. They're in the same direction. So that's our first example. Slide this up. 2. We have a car on a hilly road. So the road looks like this. When the car is here, and we're going to ignore force from the engine and brakes and stuff. Let's just go, okay, it's a roller coaster car on a hilly road. So the only thing going on is normal and gravity. Gravity is, of course, downward. This is the top of a circle. So the center of the circle is below it. Our acceleration is downward. So the normal force must be less than the force of gravity. Net force, because we need a net force downward, is force of gravity minus normal force. When we get to the bottom here, now the top of the circle is up here. Our centripetal acceleration is upward. So same amount of gravity, but now we need normal force to be greater than gravity to give us a net force and to produce that acceleration. So this net force is normal minus Fg. Remember, you don't feel your weight. You feel normal forces. So when you ride a roller coaster or you go too quickly on a hilly road, when you go over the top of the field, you feel lighter because your normal force is less than your weight. When you're at the bottom of a valley, you feel heavy because the normal force is greater than your weight. Now, if we have a car goes around a flat curve in the road, if you draw it from the top, you can't put gravity in it because then gravity would be into the page and normal out. So we usually do, if we have a car that's traveling along a road, we look at it from the side, from the front. So this is a front view. The car is coming out of the paper towards us, but it's going around a curve like this. So here's the car. So gravity's down, just like usual. Normal force is up. Well, the center of circle is over here. So we need a centripetal acceleration. That was not on the screen, sorry. We need a centripetal acceleration to the left. Well, neither of these forces points to the left. There is another force. If this force didn't exist, you couldn't even make the circle. You would keep going in a straight line, and that's friction. So in this case, the friction is what produces the circular motion. Your net force is the force of friction. If friction were to disappear, like if the road all of a sudden is covered in ice, you're not going to be able to turn. You're going to keep going in a straight line. Okay, 2 more examples, and they are building. These are getting more complicated. Let's have a string on a rope, and we're going to swing a string on a rope, a ball on a rope, swing the ball in a horizontal circle. The rope makes some angle to the horizontal. You can't swing a ball on the end of a rope in a perfectly horizontal circle with the rope horizontal because of gravity. So we're swinging it in a circle, but the rope is actually attached up here. So this is a drawing. This is the ball. This is the hand holding the rope. It goes around the circle of some radius. This would be the radius of the circle, and this is the length of the rope. This is different than the first example where the ball was onto the end of the rope and going in a vertical circle. In that case, the radius was the length of the rope. In this kind of problem, it isn't. Notice we have a triangle. If we have this angle to the horizontal, we know the length of the rope, we know the radius. We can calculate this. So when we do our free body diagram, gravity's down, of course, and the rope is at this angle. So the tension's like this. The center of the circle is not up here. The center of the circle is right here. So we need centripetal acceleration to point directly to the right. We don't have a force directly to the right, but we have a force at an angle, so we break it up into components. So we turn this diagram into FG, FTY, and FTX. So vertically, nothing's happening. So FG equals FTY. Horizontally, the only force, and it points in the direction of the centripetal acceleration, so your net force is FTX. And then last one, a car drives almost too fast around a banked curve. So a moment ago in number 3, let me flip back to it, we had a car going around a flat curve in the road. Well, when you're on traffic ramps to get on the highway, you have a banked curve. So that's a curve at an angle. So again, we're going to do a front view of the car going around the circle, but the surface is at an angle. So, of course, gravity is straight down. Normal force is perpendicular to the road surface. And If we drive almost too fast around the bent curve, that means friction is helping us out. If we drove too fast around this curve, we would go to the outside of it. We would go up. So friction must be this way. If we drove too slow, you would drift down toward the bottom of it, so friction would be the opposite way. But we're doing almost too fast. Well, here's the really annoying part. Though this is a ramp, so you immediately want to go to FGX and FGY. mg cosine theta and fg sine theta, and you switch cosine and sine because it's a ramp. You don't do that for this one because we're not going to accelerate up or down the ramp. The acceleration is towards the center of the circle. That's a horizontal acceleration. So we actually want to do our regular x and y, not to gravity. Gravity gets to stay there. We've got to break up the normal force and the force of friction. So let's do it. Fg, F norm y, F norm x, because it's up and to the left, so these are up and to the left. Now notice friction is to the left and down. So we have Ffx and Ffy. So vertically, nothing happens. The F norm y has to equal the sum of Fg and Ffy. The F norm x and Ffx are in the same direction, so they add together, and they point in the direction of the centripetal acceleration. So the net force is F norm x plus Ffx. That one's complicated. We're actually not even going to calculate that one. Okay, we might on Friday, but probably not. But this problem shows you how, even though it's a complicated free body diagram, and actually doing the math here would be a little bit annoying, but we already know what to do. It's just doing the algebra now. So draw your free body diagrams correctly and figure out what force or component of force point towards the center of the circle. That gives you your net force. And you know, you have memorized that net force equals mass times acceleration. Just for this assignment, acceleration is v squared over r.